Thermodynamics helps us understand the variation in temperature required for the thermal reduction of oxides, and to predict which element will suit as the reducing agent for a given metal oxide. The Gibbs energy is the most important thermodynamic term here. You already know that for a spontaneous reaction, the change in the Gibbs energy, delta G, must be negative. Delta G for any process at a given temperature is given by the equation delta G is equal to delta H minus T delta S, where delta H is the enthalpy change, T is the absolute temperature, and delta S is the change in entropy during the reaction. The change in the Gibbs energy when 1 gram molecule of oxygen is used to form oxides of metals can be plotted against temperature. This graphical representation is called an Ellingham diagram. These plots not only help us determine the relative ease of reducing a given metal oxide to the metal, but also to predict the feasibility of the thermal reduction of an ore. An Ellingham diagram normally consists of plots of change in the Gibbs energy versus temperature for the formation of oxides. An Ellingham diagram for oxides has several important features. Let's look at them one by one. The first feature is that the graphs for most metal-to-metal oxide reactions show a positive slope. Consider a reaction such as the formation of an oxide 2M plus O2 gives rise to MO. In this reaction, the entropy or randomness decreases from left to right due to the consumption of gases. Hence, delta S becomes negative. Thus, if the temperature is raised, then T delta S becomes more negative. Since T delta S is subtracted in the equation, delta G becomes less negative. Thus, the free energy change increases with an increase in temperature, and hence, the plots show a positive slope. The second important feature is that the Gibbs energy changes follow a straight line, unless the materials melt or vaporize. The temperature at which such a change occurs is indicated by an increase in the slope on the positive side. For example, the slope of the ZNO line changes around 800 degrees Celsius. Similarly, the slope of the MgO line changes around 1120 degrees Celsius. The third feature is that when the temperature is raised, a point will be reached where the graph crosses the line delta G is equal to 0. Below this temperature, the free energy of formation of the oxide is negative. So, the oxide is stable. Above this temperature, the free energy of formation of the oxide is positive. The oxide becomes unstable and will decompose into the metal and dioxygen. Another important feature is that any metal will reduce an oxide of another metal that lies above it in an Ellingham diagram. Thus, Al reduces FeO, CrO, and NiO in the well-known thermite reaction. But Al will not reduce MgO at a temperature below 1500 degrees Celsius. Ellingham diagrams also suffer from limitations. One is that they assume that the reactants and products are in equilibrium, which is not often true. Another limitation is that although they indicate whether a reaction can occur or not, they do not say anything about the rate of the reaction. You know that the change in Gibbs free energy of a reaction, delta G, is a measure of the thermodynamic driving force that makes the reaction occur. For a spontaneous process, delta G is negative, while a positive value of delta G indicates a non-spontaneous process. It can be seen that for a reaction where change in entropy delta S is positive, the reaction is spontaneous at a sufficiently high temperature as the magnitude of T delta S exceeds delta H. If the reactants are in equilibrium with the products, the change in Gibbs free energy can also be expressed in terms of equilibrium constant K. With the help of the equation, delta G is equal to minus RT natural log K. As you can see, in this equation, delta G can be negative only if K is positive. This can happen if the reaction proceeds in the forward direction, that is, the reactants combine to give the products. It is important to note that two independent reactions can be coupled and are feasible, provided the overall delta G of the two reactions is negative. This coupling is particularly useful for the reduction of oxides of elements. In metallurgy, a metal oxide is reduced with a reducing agent. During reduction, the metal oxide decomposes as shown here. MXO decomposes to give XM plus half O2. The liberated oxygen is taken up by the reducing agent. If carbon and carbon monoxide are used as reducing agents, then the reaction can be represented as C plus half O2 gives CO. CO plus half O2 gives CO2. And half C plus half O2 gives half CO2. As you can see, the second reaction represents the incomplete oxidation of carbon, while the fourth reaction represents the complete oxidation of carbon. The reduction of a metal oxide can thus be represented as MXO plus C gives XM plus CO, or MXO plus CO gives XM plus CO2, or MXO plus half C gives XM plus half CO2. As you can see, overall reaction 5 is the sum of reactions 1 and 2. Reaction 6 is the sum of reactions 1 and 3. And reaction 7 is the sum of reactions 1 and 4. Now, if the overall value of delta G is negative for these coupled reactions, then the reaction will be feasible. As discussed, a sufficiently high temperature favors negative delta G. The position of the line in the Ellingham diagram for a given reaction shows the stability of the oxide as a function of temperature. Metal oxides closer to the top of the diagram are unstable and are easily reduced. As we move down towards the bottom of the diagram, the metals become progressively more reactive and the oxides become harder to reduce. A given metal can reduce the oxides of all the other metals whose lines lie above theirs in the diagram. At the point of intersection of the curves for aluminium oxide and magnesium oxide, A, the change in free energy delta G becomes 0 for the reaction. 2 by 3 Al2O3 plus 2 Mg gives 2 MgO plus 4 by 3 Al. Thus, you can say that magnesium can reduce alumina only below the temperature corresponding to point A. At temperatures greater than 1273 K, magnesium cannot reduce alumina. Further, you can see that the line corresponding to the formation of carbon monoxide is sloping downwards. It cuts across the lines for many other metals. This makes carbon extremely useful as a reducing agent because as soon as the carbon oxidation line goes below a metal oxidation line, carbon can reduce the metal oxide to metal. For example, at lower temperatures, carbon monoxide is a better reducing agent for reducing iron oxide than carbon.